decay, and one type is where emissions are electrons that shoot out, and so experiments similar to J.J. Thomson's electron mass experiments, they were able to discover this type of decay and understand what's happening. And one of the things that's interesting here is the ratio of the charge to mass was actually lower, and so this was a early proof of the theory of relativity, Einstein's theory of relativity, where you have that discrepancy in what's going on with mass, which we'll get into great detail. A mass of an object increases as the speed becomes comparable to the speed of light, and this was starting to be seen here with these beta particles. So a neutron decays into a proton in a nucleus, and an electron and an anti-neutrino are released. And so if we have beta decay, that neutron itself becomes a proton, and again, this will happen in a nucleus if there's too many neutrons, and that neutron will become a proton. So what we see here is we have now a proton, same atomic mass here that we see, but now we have +1 charge. And so we know with conservation of charge, if we started with 0 charge, we should finish with 0 charge. So what happens is that proton, or the neutron, becomes a proton and then shoots out an electron. And therefore, with that electron plus the proton, we still have neutral charge. If we added them up, we'd still get 0. So we start with 0, we finish with 0. And then we finish with an anti-neutrino. An anti-neutrino shoots out. And the way that you can remember, hopefully, an anti-neutrino, there's a bar on top of the V representing anti-neutrino. And so as the particle shoots out, an anti-neutrino must be released as well. And the reason for that anti-neutrino is very, very important. In Enrico Fermi, is part of that, and we'll talk about that too. In beta minus decay, here's an example here where we have a carbon nucleus, carbon nucleus, carbon 14 in this case. And what happens is this has too many neutrons for as many protons as we have. So one of the neutrons becomes a proton. And when that happens, we go from a +6 charge to +7 charge. And then again, for conservation of charge, an electron must shoot out. And as an electron shoots out, an anti-neutrino also shoots out. And so the arrow represents the transition here. We go from this carbon atom, carbon 14, to this nitrogen atom, and then we have that there. So again, this is called beta minus decay, where there's too many neutrons for the protons there. Neutron converts into a proton, and the anti-neutrino is released. So why was another particle needed? Well, this was first postulated in 1930 by Wolfgang Pauli to preserve conservation of energy, conservation of momentum, and conservation of angular momentum in beta decay. There was a major issue here as we had a nucleus and an electron, shoots out. Conservation of momentum, right? We have an issue here with the nucleus itself. We know that if we had a cannon, we have a cannonball that shoots out to the right. The cannon's got to go to the left, and so it turned out that it did not look like energy was conserved, momentum was conserved, angular momentum was conserved. So they were almost questioning that. Okay, maybe conservation of energy, momentum, angular momentum are relevant here, so they proposed that there was this other particle that would help show the conservation. And it wasn't until later that they actually discovered this particle. Right, so in beta decay, a proton turns itself into a neutron and then releases a positron. And we can write out the full equation here. We start with a proton. So we're starting with a +1 or positive E charge, right? So we should finish with that. What happens is when that proton turns into a neutron, it shoots out a positron. It's a positively charged electron, and that's the antiparticle of an electron.
Yes.
Actually shoots out a neutrino. So remember before where we had the electrons shoot out with an anti-neutrino that shoots out with a neutrino. And so we can write out this equation here. We have helium turning into hydrogen, and one of the protons of the helium turns into a neutron, so a proton into a neutron, and therefore shoots out a positron and a neutrino. And again, a neutrino is released, looking at conservation of energy and momentum. Okay, so one of the things that we want to picture with the nucleus is the fact that with the nucleus, itself, if there's too many protons and neutrons, we kind of anthropomorphize it. It's going to want to shoot out an alpha particle, and this alpha particle is 2 protons, 2 neutrons, and typically what happens then, when it decays, the nucleus itself is in an excited state, and so what it needs to do is shoot out a photon, and it'll be at a lower state, and then it can shoot out another photon and go down to the ground state. And so over that progression, shoot out an alpha particle, and then you have the 2 gamma decays there. The neutrino and antineutrino were proposed to make beta and positron decay, a conservation of energy. And so they were proposed, and then they were discovered. And these particles possess energy and extremely small amount of mass. They pretty much don't interact with anything. We have billions of them going through us right now, coming from the sun. And they don't interact with matter significantly at all. All right, so if we take a look at this one, this H16, we have an element decaying into another element here, and as that happens, an alpha particle shoots out, and then it's in an excited state, so then a gamma ray shoots out. And so what's also possible, though, is that the alpha particle could be shot out, and then it could go to the ground state. And so if we actually subtract those values there, or add up those values, they should be 4.45 on this side as well as this side, because just like we had before with electrons going to lower energy levels, we can see the similar thing here. So so let's go ahead and calculate the energy, or I'm sorry, the wavelength of the photon of this 0.186 megaelectron volt photon that shoots out. And so I'll go ahead and pause the clip and go ahead and calculate that. When you're ready to check, you can hit play to continue. Okay, so we'll convert our electron volts to volts. This is mega, right? So we convert to electron volts, and so we'd have our joules value here. We can figure out the frequency of this photon, very high frequency, the highest out of the different electromagnetic waves, right? And that shoots out, and we get a wavelength of 6.68 times 10 to the negative 12 meters. So gamma radiation, we have where, how did we actually discover it? What's kind of neat about this is, remember with a double slit, we would send light through and it would diffract. For gamma rays, they're such small wavelengths, you have to have a much smaller gap, and so they actually had these shot toward crystals, and they got diffraction patterns, and with those interference patterns, they were able to detect that these were actually gamma rays coming in this radiation there. And so you can see this here, an example of
hold on, you gotta add
cobalt turning into nickel, and then shooting out a gamma ray.
It's a strap on those.
So gamma radiation, again, is electromagnetic in nature. The nucleus, keeps the same number of protons and neutrons. It's just, going from an excited state to a lesser, or to a lower state, and and then shoots out a high energy photon, as we calculated there. So again, and I keep getting radon and radium mixed up. That's right. This is radium to radon here, and the radium shoots out a alpha particle, and then it's in an excited state, and then
shoots out a gamma ray and then decays or goes back down. So what's really interesting about this is the nucleus itself has energy levels. You know, after decay, it may be in a ground state or may not be, because you know, depending on the energy given to that alpha particle, you know, if it gives all that energy to the alpha particle, it's going to shoot out with all of it. But maybe that alpha particle is not having as much energy, and then the gamma radiation makes up for that and goes down to the ground state. So in this one, H17, what is the wavelength of a photon given off by a nickel nucleus when it drops from the 2.158 megaelectron volt level to the ground state? If you want to pause the clip and give this a try, and then when you got that, you can hit play to continue. Okay, so we see here we can convert a value to joules. Find the frequency, 5.212 times 10 to the 20th hertz, and the wavelength of this is 5.76 times 10 to the negative 13 meters, and that's this transition from the color we can see from here to here, right? What could have happened though, it could have gone from here to here, then from here to here, right? So you'd actually have two separate gamma rays. We'd subtract this value from this value, figure out, you know, what kind of photon to shove out, and then this value 1.322 down to 0 would be two gamma rays instead of one gamma ray there.